So welcome back to part 5.4. I promised that we would say something about fluctuations of the membrane potential caused by stochastic spike arrival. So far we calculated the mean. I said a little bit about fluctuations, but the question arises, can we calculate the fluctuations? Now, fluctuations of the membrane potential are indeed observed in vivo. So it's interesting to know a little bit how these variances, the fluctuations, could possibly arise. And to do so, we develop a model. So we have already seen in the previous part that synaptic current pulses caused by stochastic spike arrival add up and give rise to some current, which can be described as a mean plus a fluctuating part. Now this current is injected into the differential equation of a passive membrane and gives rise to a fluctuating potential. The question then arises, can we say something about the mean of this fluctuating potential? And we did so in the previous lecture. But moreover, can we say something about the typical size of these fluctuations? And that's the topic for now. So if the mean at a given moment in time, at time t, is something like u bar, or expectation of u of t, then we are interested in these fluctuations of size delta u, and we look at the expectation of these fluctuations. Now, the specific situation here is that of a current. You can think of a step current like this, but the input was a fluctuating version of this step current. Something like this. Now, this is low-pass filtered by the differential equation and gives rise to this kind of fluctuating membrane potential trajectory. And the question is, can we calculate these fluctuations? In the previous lecture, I've already said that any filtered spike train can be treated with a formalism where I have an arbitrary filter f. This is the spike train, including the sum over all spike times. And if you look at the mean, then this is the mean of the spike train, and for the case of a homogeneous Poisson process, this would be the rate. That's the rate of this spike train. We don't consider k independent inputs anymore. Let's consider just one single input spike train, S of t. Now what we are interested in now is the autocorrelation. So my value x at time t might be related to the value at a later time t prime. Now let's see whether we can use the same kind of procedure to write this down. So for x of t, I take the formula over here. I say this is integral dt prime and then f of t minus t prime s of t prime. Now, for x of t prime, now I have a problem because I've said this is t prime, so let's call it t hat. Okay? So, for this, I take the same formula again. Let's write it down. It's another integral dt double prime, and then what used to be t is now t hat, so it's t hat minus t double prime s of t double prime. And at the very end, I will consider the expectation. Now, the expectation concerns only the spike trains. The spike train is stochastic. Spikes can arrive here or there or there or there. Spikes are, let's assume, generated by some Poisson process. So I would like to bring the two stochastic processes together. So let's write S of t prime, S of t double prime. Then I have the integration signs, everything is linear. I can pull out the integrals in front, dt prime, dt double prime, and I have f of t minus t prime coming from here. And I have the other filter t hat minus t double prime. Now what about the expectation signs? The expectation signs can move inside. Taking the expectation is a linear procedure. I can pull it inside, and the only stochastic part are these spike trains. So this is the result. The correlation at time of my signal x at time t with the same signal at a later time or earlier time t hat, expectation, that's the autocorrelation, is given by this formula. Now x is some arbitrary signal here, but x could be my membrane voltage. So I could take U of t. If the membrane is a passive membrane, it can be described as a linear filter. Now there's one thing which appears here on the right-hand side, and that's the autocorrelation of the spike train. This is my spike train. I have a spike here and I have a spike there. And the question is can I say anything about the probability that the spike here at time t is correlated with a later spike at time t double prime? This is my spike train. Suppose that the probability of firing in each time step is Pf rho 0, a constant rate, times delta t. So we are in the case of a homogeneous Poisson process. Now, Poisson process means that the firing probability in this time step, let's call this time step n, is completely independent from the probability of firing in some other time step k. So, the probability of having a spike in step n and in step k, now these are different time steps, n is not equal to k, then the joint probability having a spike in step n and a spike in step k is just Pf times Pf, or rho 0 times delta t, another rho 0 times delta t. However, nobody said here that n and k must be different. I should also consider the probability of having a spike in step n and in step n. Now this sounds kind of stupid. Well, if I have a spike in step n, I know that I have a spike in step n. So the probability of having a spike in step n is just Pf. The probability of a spike in some time step is rho 0 times delta t. So what we learn from this simple argument is that we have to distinguish the two cases. The case where we talk about spikes in the same time step, and if I have a spike in that time step, I know that I have a spike in that time step. And the normal case, that the time steps are different. Now let's take the limit delta t to 0. And if we do that, we get the autocorrelation function of the homogeneous Poisson process. So, if the time t and t prime, if the two times are not the same, then I just get the rho zero squared. However, if t and t prime are identical, then I just get rho zero. So the autocorrelation is a density. It's sort of a double density. I have to integrate twice to get back something similar to a probability. Now let's put things together. We said for some arbitrary signal, if there's a filtering process, we can calculate the mean and the fluctuations. We can calculate the mean and the autocorrelation. The fluctuations, if I evaluate this at the same time, then this gives the size of the fluctuations. It's the autocorrelation at zero delay. In order to calculate that, we will need our S of t prime, S of t double prime, which we can calculate for Poisson processes. Now, a passive membrane is what you would find, for example, in the leaky integrated fire model in the sub-threshold regime. In other words, for stochastic spike arrival, we can, in the case of a passive membrane, we can predict the amplitude of the membrane potential fluctuations. We can do calculations and predict analytically what we should see. And this is in particular true for the leaky integrated fire model in the sub-threshold regime. So, if I have a leaky membrane, more generally, if I have some passive membrane, if I have a passive dendrite, then I can calculate the fluctuations of the membrane potential in the presence of stochastic spike arrival. Now, real neurons have a threshold, and the simplest model of a neuron with threshold would be a leaky integrated fire model. In the subthreshold regime, we can use the results of the passive membrane, and we simply have to add a threshold. And that's what's going to be the topic of the final lecture of this week. Please take a moment to look at the quiz before you continue.